Hello and welcome. Today we're going to be cracking open a really powerful tool in chemistry. It's called electrolysis. It's a process that lets us break down chemical compounds that are normally incredibly stable. So let's just dive right in. All right, let's start with a bit of a puzzle. We all know table salt, right? Sodium chloride. It's super stable. You put it on your food. But think about what it's made of. Sodium, which is a highly reactive metal, and chlorine, a poisonous gas. So how on earth do you separate them? You can't just heat it up or crush it. That won't work. You need a much more powerful method. And the answer, as you probably guessed, is electrolysis. The name itself actually gives us a big clue. You've got electro for electricity and lysis, which is just a fancy word for splitting or breaking apart. So we are literally using electricity to split a compound. This is the key we need to solve our little puzzle. So how does this whole thing actually work? Well, first, we need to understand the setup. It's called an electrolytic cell. Let's take a look and break down what's inside. Okay, so this diagram is going to be like our whiteboard for today. It shows all the key players. You can see we've got three main parts. First, you have the liquid in the beaker. That's our electrolyte. Second, see those two rods dipping into the liquid? Those are our electrodes. And finally, at the top, you can see they're connected to a power supply. Now, the electrolyte isn't just any old liquid. This is really crucial. For our example, we're using molten sodium chloride, and it has to be molten or dissolved because we need its particles, we call them ions, to be free and able to move around. See, if it were a solid, those ions would be locked in place and absolutely nothing would happen. Think of it like creating a sea of charged particles that are free to swim about. But wait, where do these charged particles, these ions, even come from? Let's zoom right into the atomic level. As you can see here, the sodium atom, which is a metal, gives away one electron to the chlorine atom, a non-metal. This simple transfer creates our ions. The sodium atom becomes a positive sodium ion, Na+, and the chlorine atom becomes a negative chloride ion, Cl-. And just like that, our molten electrolyte is now full of these free-moving positive and negative ions. Okay, so we've got our setup. We've got our sea of free-moving ions. What happens when we flick the switch and turn that power on? Well, this is where the action really starts. The moment that power is switched on, one electrode becomes negatively charged and the other becomes positively charged. This sets the stage for everything that follows. Now, just remember, the most basic rule in science, opposites attract. So the positive sodium ions, we call them cations, they start moving towards the negative electrode. And at the exact same time, the negative chloride ions, we call those anions, are drawn towards the positive electrode. It's like a great migration of ions. Now, listen up because for your exams, it is absolutely vital to remember which electrode is which. This is such a common place to lose marks. But don't you worry, I've got a simple trick to help you remember. Just think of the word panic. Panic is just a super easy way to get the electrode charges right every single time. It stands for positive anode, negative is cathode. Simple as that. Seriously, I recommend you just scribble this down on your exam paper as soon as you're allowed to start. Panic, positive anode, negative is cathode. It'll save you from a lot of confusion, trust me. So our ions have all migrated to their oppositely charged electrodes. But they don't just, hang around there. This is where the real chemistry happens. This is the climax of our process, where brand new substances are actually formed. This slide shows us exactly what's going down. Let's look at the negative cathode first. The positive sodium ions, Na+, arrive there. Now the cathode is rich in electrons, so each sodium ion gains one electron and turns back into a neutral sodium atom. And just like that, we've made pure sodium metal. Now, over on the other side, at the positive anode, the negative chloride ions, Cl-, show up. They each lose an electron to the anode, and then they pair up to form chlorine gas. See, we've just made chlorine. Now, these processes of losing and gaining electrons have special names. And to remember them, here's another essential exam mnemonic for you. Oil rig. It stands for oxidation is loss of electrons. That's what happens at the anode. And reduction is gain of electrons, which happens at the cathode. Oil rig and panic are your two best friends for any electrolysis question you'll ever face. Okay, let's just pause for a second and really nail that key takeaway. At the cathode, we get reduction and we form sodium metal. At the anode, we get oxidation and we form chlorine gas. We did it. We successfully used electricity to break down stable old sodium chloride into its original super reactive elements. You know, this isn't just a cool classroom experiment. Electrolysis is actually a cornerstone of modern industry. It's responsible for making so many products you probably use every single day. Let's look at a few examples of why this really matters. Just look at these applications. The aluminum in your soda cans, that's extracted from its ore using electrolysis. The chlorine that purifies our drinking water, yep, produced this way too. And if you've ever seen a shiny silver-plated spoon, that's done through a process called electroplating, which is just another form of electrolysis. As you can see, this is a massive industrial process, and that's exactly why it's such a key topic in your syllabus. So, we've seen how electrolysis uses electricity to break things apart, to deconstruct them. And that leaves us with a final thought to ponder. If we can apply electricity with such precision to break chemical bonds, imagine what amazing new materials and technologies we could build by reversing the process and using electricity to precisely form them. That's a big question, and one for another day. Thanks so much for joining me.